So what is the latent Dirichlet allocation model? It is a popular model for modeling a collection of documents or articles. When we model documents or articles, we ignore the order of the words. So for each document, we're just going to summarize how the word frequency in each of the document. Suppose our vocabulary size is V, meaning we have capital V words. Then for every document, we can just represent it by a vector of length V, and every entry denotes how many times that corresponding word appearing in that document. And so the N documents will be represented by a V by N table and a matrix, and each document has a feature of length capital V. So for our later downstream analysis, we have to carry in that V-dimensional feature for each of the document, which is really high dimensional and also probably not necessary. And so LDA is a modeling technique try to provide a more compact representation of a collection of documents. How to model those documents? First, let's introduce the concept of topics. So every topic is basically a distribution over words, meaning for topic 1, it is a vector of length V, and every entry represents the probability of the corresponding word will appear in a topic. So those V entries for topic 1 summed together should be 1. And you can think about how to use topics to generate an article. For example, suppose we pick topic 1, then we know our article, it belongs to topic 1, and the article has 200 words. Then we can just first generate a word based on this multinomial distribution with length V, and suppose that's a second word, so put it in that document. And then we use the same mechanism to generate the second word and go on until we generate all the 200 words. So topic basically is a distribution over words. Naturally, topics can be used to categorize different documents. For example, we could have a topic related to business, topic related to technology, or topics related with sports, if we're talking about a collection of documents from Google News, for example. And the topics are different because under different topic, the distribution over the words will be different. For business topic, we would expect business-related words will have higher probability to appear, and for sports-related topics, we would see more sports-related words. Following what we just discussed before, it is very natural to model a collection of documents as a mixture of topics. So for example, we can introduce a latent variable Z1 for document 1, and a latent variable Z2, and also a latent variable Zn. And each of the Zi's will take value from 1 to k. Suppose Z1 is equal to 1. That means for our document 1, its words can be regarded as IID draw from the distribution determined by this topic 1. And maybe for the last document, Z sub n, if it's equal to 2, that means all the words in document n can be regarded as an IID draw from that multinomial distribution determined by the last topic. And we can also learn a mixing weight, which is k by 1, which basically model the distribution of those latent label Z1 through Zn. However, LDA moves one step beyond this simple mixture model. Instead of modeling every document from one and only one topics, in LDA, every document actually is a mixture over k topics. It is natural because suppose we have a news article talking about the IPO of a tech company, then we're going to expect some part of this article will have a lot of technology-related words, so it's really related with a technology topic. But we also expect some part of the this article will be categorized as a business topic. So instead of introducing Z1 through Zn, we are going to, even for document 1, we're going to introduce additional V latent variables, one for each word. So we're going to introduce the latent variable Z will be organized as a matrix, and the same as this word frequency. So it is also V by N. For example, for the first document, we have the latent variable for each of the V words. And they could be different because each of the words could follow a different topic. And then instead of still we can learn those topics, then instead of learning one mixing weight over the K topics, we're going to learn for every document, we can learn a mixing weight pi 1, pi 2, and all the way to pi n, which is exactly what's plotted here. So for every we have for a collection of documents, and once we do our LD analysis, it will output K topics. Each topic represents a distribution over words. And in addition, we're going to have this mixing weights and matrix. It is K by N. And each column represents the mixing weight over the K topics for each of the documents. Now you can see that what I mean by compact representation. Previously, we represent our topic by a V by N term frequency table, but now that the documents are compactly represented as a K by N matrix. So now for every document, and the corresponding feature vector is no longer a V by 1 vector, but a K by 1 vector. So for our any downstream analysis, we can use this K-dimensional feature for all the documents. But because of this whole model is sort of a mixture over mixture model, the EM algorithm we introduced before won't be able to solve the MLE and other parameters. And so we have to use a variational EM. I didn't put down the reference for LDA model, but it's such a well-known model. You can easily find the original paper. In addition, here I grab a picture from a review paper by one of the authors of the original LDA model. Here, for example, in this case, we have 4 topics, and for particular document, we could see different words actually may be drawn from different topics. So at the end, what we get, we can summarize the information stored in this article by just the frequency over the 4 topics. Well, in this case, we don't have any words from the green topic.